Now let us talk about convergence. Because you have sum going from minus infinity to plus infinity, you need to worry about whether this quantity exists or not. There are many criteria for convergence. We will use a criterion that was used in the Laplace transform case. So, convergence actually depends on the criterion used. And we will use exactly the same criterion that was used in the Laplace case. And the convergence criterion that was used in the Laplace transform case was what was the criterion that you were using for the existence of the Laplace transform? The criterion that I hope at least now it rings a bell. And what is then some other convergence criterion that this terminology triggers that you may have heard of? In terms of integrals, remember this I am recalling what you may have learnt in Laplace. The other criterion that could have been used is uniform convergence, whereas in the Laplace case we used absolute convergence as the criterion. We will use absolute convergence criterion for the Z transform case. There the absolute convergence meant absolute integrability, whereas here absolute convergence would mean absolute summability. Therefore, x of z is defined as n going from minus infinity to plus infinity, x of n z to the minus n. The absolute convergence criterion demands that mod x of z less than infinity. So, this is the criterion for absolute convergence. So, let us examine mod x of z. So, this is the absolute value of the summation over all n x of n times z to the minus n, and then since absolute value of the sum is always less than or equal to sum of the absolute values, you have this is less than or equal to n going from summation over all n mod x of n mod z to the minus n. We will now let z equal to r e to the j omega, and hence this summation becomes r to the minus n, r being a non-negative quantity, then e to the minus j omega n. All I have done is I have replaced z by e to the j omega, and this of course is 1 and does not play any further role. So, now we need to look this up. We will break this into two parts. So, this can be written as n going from 0 to infinity mod x of n r to the minus n plus n going from minus infinity to minus 1 mod x of n r to the minus n. First term remains as it is, and in the second term we will replace n by minus L, and then we will relabel L as n once more. Therefore, this is nothing but n going from 1 to infinity magnitude of x of minus n, and this is r to the n. And if you look at the way the summation has been split, what we have done is we have broken the sequence into two parts. This is the causal part, namely the sequence with indices ranging from 0 to infinity, and this is the anti-causal part of the sequence, where recall we are using the term causality that was introduced in terms of systems. We are applying it to a signal. Signal is called causal if it is 0 for n less than 0, and anti-causal if it is 0 for n greater than or equal to 0. Now, let us look at each of these terms. So, let us look at causal part to see what that behavior is. Suppose, let us assume that there exists a certain R naught for which the first part exists, right. So, suppose there exists R naught such that the first term converges. Let us assume this. Then we want to ask the question, what about values of R that are greater than R naught? If you know that the first term converges for a certain R naught, what can you say about the convergence for all values of R that are greater than R naught? The sum will converge, because if you consider a value say R that is greater than R naught, then this term, the weight that you apply to the sequence decays more rapidly, right, because if you have R greater than R naught, then R power minus n will be less than R naught to the minus n. Therefore, the terms are weighted down more and more heavily. Therefore, if the series converges for R naught, then for all values of R that are greater than R naught, the series necessarily will converge. And the theorem that is used to establish this is, intuitively you see that this is true, but the precise theorem that is used is the comparison test. So, series comparison test is used to establish the result. So, we can see then the series converges for all R greater than R naught, because R power minus n will be less than R naught to the minus n. Therefore, if a certain radius exists for which this series converges, then for all radii that are greater than this, the series is definitely bound to converge. Now, very similar arguments can be made for the anti-causal part. Again, let us assume there exists an R naught such that the second term converges, then what can you say about the convergence for all radii that are smaller than this R naught? The series will definitely converge, because remember, now we are looking at R power n. Therefore, any radius that is smaller than R will decay faster, and hence by the comparison test, if the series converges for R naught, series will necessarily converge for all values of R that are less than R naught for the second term. So, the series converges for all R less than R naught, because R power n will be less than R naught power n. Now, let us assume, let R1 be the smallest radius for which the first term converges. Similarly, let R2 be the largest radius for which the second term converges. So, if there exists an R1 for which the first term converges, and if there exists an R2 for which the second term converges, then the complete series, which involves both the first term and the second term, will converge when you have mod z between R1 and R2. Okay. So, hence x of z exists if you have R1 strictly less than mod z strictly less than R2. So, clearly this supposes that R2 is larger than R1, because you are looking at the intersection of two regions of convergence. For the first part, you require mod z to be greater than R1, and for the second part, you require mod z to be less than R2. Therefore, these two regions must overlap, which means R1 must be strictly less than R2. So, this implies that the region of convergence is an annular region. And R1 can be as small as 0, R2 can be as large as infinity. Therefore, the region of convergence as far as Z transform is concerned is in general an annular region with radii R1 and R2, and this is the region where in general the transform exists. And the reason why you have the region of convergence to be an annular region is because the convergence criterion that we have used is the absolute convergence criterion, and the absolute convergence criterion boils down to the parameter R. This is the reason why the region of convergence is an annular region. So, if you recall your Laplace transform case, there you had x of s. So, this was integral minus infinity to plus infinity x of t e to the minus st dt. Again there you used absolute convergence. Therefore, you required this. So, this was less than or equal to mod x of t, and this was written as e to the minus sigma t e to the minus j omega t. You had to take mod, this term goes off. Therefore, the convergence of the integral was dictated by the parameter sigma, and sigma is the real part of S. That is why there the convergence happened between vertical lines, because the parameter governing convergence was the real part of S, whereas here the parameter influencing convergence is the radius r. That is why what is happening in the Z transform case is between two circles. What was happening between two vertical lines earlier is now happening between two concentric circles. And we saw this example. So, this was 1 by 1 minus a z inverse. So, this was mod z greater than mod a. In this case, R1 happens to be not a, but mod a. Remember, a in general is a complex number, whereas R2 is infinity. Similarly, if you had x of n to be minus a to the n of minus n minus 1, again you had 1 by 1 minus a in the same algebraic expression, but in this case it is mod z strictly less than mod a, and here R1 is 0, R2 is mod a. So, just to illustrate the fact that R1 can be as small as 0 and R2 can be as large as infinity, we have already seen examples. Just to give some more insight into this ROC, for rational x of z, recall that rational means x of z is of the form b of z over a of z, ratio of polynomials. For rational x of z, the ROC will be of the form R1 strictly less than mod z, strictly less than R2. For rational transfer functions, this is how the ROC will be, and the ROC will be bounded by poles. So, this is exactly the same as what was happening in the Laplace transform case. In the Laplace transform case also you would have had sigma 1 strictly less than real S strictly less than sigma 2. There also you had the ROC bounded by poles. And suppose x of n is 1 by mod n plus 1. So, this we will just note the fact that if you want to take a guess about the Z transform of this, what would be your guess? Yeah, very good. It does not exist, and the reason why it does not exist is Okay. Um, suppose I had 1 over n plus 1 for n greater than or equal to 0. Remember, now this exists for all n from minus infinity to plus infinity. This is a two-sided sequence. Your answer is correct, but I am trying to understand more as to what made you conclude that. Suppose I had 1 over n plus 1 for n greater than or equal to 0. Then if I had asked you about the Z transform, what would be the answer? Okay, we will look at similar examples later very soon, and maybe you will see the reasoning that we are going to make in those cases will apply here also. No, that's not right. Okay, so here the Z transform does not exist. We will not, we will make a remark later about sequences like this. And suppose you had a sequence like this, 1 over n squared plus 1. The ROC is mod z equal to 1. So, this exists only on the unit circle. So, we will not further get into details of sequences like these. Just want to make you aware that there are cases like 1 over mod n plus 1 for which Z transform does not exist, and there are sequences like this in which the annular region has degenerated into a circle where R1 equals R2. That is all. And if you ask the mathematicians to define R1, they will define R1 like this. And this stands for lim sup. So, this stands for lim sup, and R2 will be lim inf of n tending to plus infinity x of minus n 1 over n. So, these are the definitions of the two radii, and this is the Cauchy-Hadamard result. Again, we will not use any of this. If you did not know what lim sup and lim inf were, you need not be concerned whether you will be asked to draw upon that knowledge to solve problems. We are considering only the class of rational transfer functions, and they are the simplest class, and moment you evaluate the poles and zeros, you can always be guaranteed that the ROC will be bounded by poles. Question, yes. Very good. Yeah. Yes. Whereas for rational transfer functions, we need the two radii will be distinct. So, I just want you to be aware of these formula, but our problems are much simpler that we will not have to use any of this.